and welcome back to another part in this series where we're going to be creating an FRC Slapdown intake for the 2020 game. Just a quick recap from what we did last video. We designed our intake master sketch. So we've planned out how we want our ball to come into our robot, and we've also planned out, based off that, where our rollers need to be when the intake is outside of the robot, where our rollers need to be when the intake is inside of the robot, and hence where our pivot point needs to be. So this guy right here. What we're going to do now is we're going to sketch the plate of the intake that comes out of the robot. After that, we'll be sketching the gearbox plate for bringing the intake in and out, since that's going to be a relatively high torque gearbox that needs to carry an arm that weighs quite a bit, so it's going to have a lot of force acting down on it. Yeah, let's sketch this plate. So I'm going to open up this part that I've made already. And yeah, I've just got a regular Power Studio. This is the Power Studio. This is the assembly. Once we've got parts in our Power Studio, we can start to use the assembly. But for now, we're going to stick to the Power Studio. Okay, so click N. The first thing I'm going to want to do is bring in my master sketch that we drew in the last video. So the way that you do that is use the derive feature. So we'll use the derive feature, and we need to go and find the master sketch. So that's going to be other documents owned by me. It's going to be in 2025 tutorials. I mean, this is just my directory, but put that guy in, and you can see he's in there, so that's good. Another thing is that you can move this guy around. Right now it's aligning the origins of this Power Studio and this Power Studio. But you can say I want it to main to a main connector, and then put the main connector there, and move them around. But ideally you don't have to do that. You can see it moved away from the origin there. Ideally you don't have to do that, because if we just keep it as base origin, it makes everything nice and simple. Let's get rid of this guy. Cool. So now I've got my sketch in here. If I was to change something here, for example, bring the pivot point in a bit, up a bit, let's say 170. Just brought it up. You might want to actually these might not be the parameters that you want to be changing. For example, your angle difference is not as nice to have as being able to change the horizontal and the vertical position of the pivot, just in case our pivot is not in a great spot on the robot. So I've deleted the angle dimension, and I've dimensioned now the pivot horizontally to our bumper. So now I can move that guy 60 mil over. I don't really care about the angle that I'm bringing it back. It doesn't matter to me as much. Though it will matter later when we calculate the gearbox that operates the pivot, right? Because we have to know how much we'll be rotating it. So then we can do a driven dimension for that, which is what I've done there. When it's grayed out, it's driven, so you can't actually change it. It's just for show. So we have a bit more data about our sketch. So once that's done, you can actually version this guy, right? And what that does is it creates kind of like a checkpoint. I think I might have explained it in the last video. I don't remember. But essentially, the create version creates a checkpoint in our CAD, and we can go back to, any checkpoint in our CAD. We can revert to it, and it just gives us a bit of control over the history of our CAD, just in case something goes wrong in the future and we want to go back to where a design was good or before some changes happened. But because we've checkpointed it now, it's going to tell us, hang on, there's a change in the version of our link document, which our link document is this guy. Before this wasn't here. If I click on this, you can see that Master Sketch has changed from V1 from when I put it in the derived initially to V2 when I versioned this guy to V2. So I'll update him, and we should see the pivot point move. Fantastic. Um, so now what I want to do is I want to draw the plate, right? So I'm going to start a sketch. I'm going to start him on the right plane. It's on the same plane as the derived sketch, so that's nice. And I'm probably, the first thing I want to do is I want to pick up the points that are used for the rollers and are used um, for the rollers and for the pivot point, right? So how do I do that? I can use the use function. Use, project, convert. What does that do? It projects edges or faces of an existing part or sketch onto the active sketch plane. So I'll click on this guy, or you can click U instead to select it. I'll pick him up, pick him up, pick him up, and him, right? So now I've got those points in this new sketch, in sketch one. To demonstrate that, you can see if I was to hide sketch one, hide derived one, I'd have nothing. But if I was to show sketch one, you can see those points I just clicked on show up. So they now exist on sketch one, and they are related to derive one. If I was to update my master sketch, update them this way, how we just did, sketch one would also move. Those points would also move, which is great for when I want to do some fine tuning later. If I've realized I made a mistake for whatever reason. So I guess the first thing we can start on is we know that we're going to be using a dead roller. So what does it mean to be using a dead roller? So if we go into here, we can see the difference between a dead roller and a live roller. You can see in the right one that you have a shaft. This silver part here represents the plate that the shaft is running in, and the plate has a bearing in it. So the shaft, you can see what's intended here is the pulley. This green pulley is actually driving the shaft, and the whole shaft spins, and hence so does this black wheel. This is a cross-section drawing of the wheel, just so you can see the internals. Alternatively, what you can do instead is a dead roller, where instead of the shaft spinning, the shaft is directly bolted onto the plate, as you can see here. And this green part here, you can't see it so much, but that's a pulley, just like this guy is a pulley, and a belt runs to it. This guy is also a pulley. The belt will spin this pulley, hence spinning only this pulley and the wheel. So the shaft doesn't spin. And the benefit of that is, one, you don't have to push the shaft through here, put on all the wheels, push it further through to the next bearing. Instead, you can assemble it off the robot and then slide it in and secure it by putting in these two bolts and threading them in. And additionally, you get a much smaller hole in your plate. You can see the bolt diameter is a lot smaller in this bearing. And what that means is when your robot is involved in some collision with a wall with another robot, there's less chance of your part breaking because there's more material in the plate and the hole is essentially smaller, right? So that's what we'll be doing. They have their benefits. Each one has their benefits, and it really comes down to what you want to use, what resources we have available to us, and what's right for the application, right? So, because we're using a dead roller, I'm going to go back into this sketch one, and I'm going to, every part where there's a roller, I'm going to put a 5mm bolt hole. So 1, 2, 3. They're all going to be equal to each other. So we can click E to make them equal. And we're going to dimension them to 5mm. 5.1 actually, because we need to make a clearance hole for the bolt. The next hole that we're going to probably want to use is this pivot point. We're probably going to have a hex shaft as our pivot point. So let's do that, right? In order to use a hex shaft, we need to have a bearing. Well, essentially, what I'm thinking is we're going to have a big sprocket here. And that big sprocket is going to have a little sprocket over here. There's going to be a little sprocket there that's going to be driving it. And in order to ensure that we don't have backlash, so what is backlash? That means that we're spinning this guy, the chain is moving, but the connection between the big sprocket and the plate we're about to make is they're not directly coupled. They're coupled through the shaft, for example. So this big sprocket is able to move without the plate actually moving, and that's bad because it means that software inherently has less control over our intake. We want to reduce backlash, hence giving software more control and improving our reliability. So our sprocket is going to be directly bolted onto our intake plate. If you're not sure what any of this means, I think you'll realize later how it all works once we get everything assembled. But essentially what I'm trying to say is, I'll delete all these guys. Why won't they be deleted? There we go. What I'm trying to say is we can have a bearing hole here. So if you want to know how big a bearing is, a hex bearing, we use 1/2 inch hex. If I go ball bearings, 1/2 inch rounded hex, right? This guy, or I suppose you could also use this guy here. It doesn't matter because their outer diameter, their OD, is 1.125 inches. So let's do that. 1.125 inches. Essentially, what I'm trying to do in this sketch is I'm trying to map out where all of the holes in our intake need to be, and then I can map the plate around those holes. The holes are the most important thing, and then the perimeter can be dimensioned off those holes. The next thing I probably want to do is map out where the sprocket is going to bolt to. So I can go to sprocket. Let's say I'm going to use a 35 sprocket for this application. I'm going to use, I don't know. The bigger the sprocket, the better, because it means that you have less backlash. Because essentially a the same change on this side of your gearbox, on here, the same change in angle on this side of your gearbox, if this sprocket is bigger, it'll result in a smaller change in angle. So if you have backlash here, you have less of an effect on the angle on this side, right? So I'm going to use a 36, right? But we need to know where these holes are positioned. Now, how do we find that out? We can go into the drawing for the 36 tooth plate sprocket over here, right? So what's where do we find the bolt circle? It doesn't say. No worries. So alternatively, does it not say? How strange. Okay, so alternatively what we can do as well is we can go into here. You should have MKCAD inserter, and we can put in the WCP code, like the product code for it. This guy? Nah. Oh yeah, there we go. 0983, right? So once we have that done, we can now measure, all of these holes are kind of like on the same bolt circle. So I'll pick this guy and this guy, and we can see their parallel axes distances. So this dimension here is 50.8, right? That's actually 2 inches, because an inch is 25.4 millimeters, so 2 inches. So I'm going to draw a 2-inch circle around here, right? I can click on this guy, Q, construction line, because it only serves as like a reference for my, for my bolt holes. And let's say I want one, this looks like I can use 4 equidistant. Maybe I'll use more than 4. So I'll draw one hole. How big are these holes? These holes are 5 mil, right? So I can do 5 mil hole, and that's constrained to this guy because I drew it on that line. And what I'm going to do is circular pattern on this guy, move that center point over here, and where's this guy? Okay, this is how many holes I want on my circular pattern. So I can increase this, now I have 5 holes, right? That's not quite what I want. Instead, what I'll probably want is 6, maybe? Is that right? Think that's good. Yeah, we can do 6 holes. Okay, so I've got that. Now it can still spin, so I need to constrain it somehow. How am I going to constrain it? I'll figure it out later. Actually, it doesn't really matter. I suppose I could make these two vertical. So like last time, we just click V. But it doesn't matter. It could matter if something is going to hit, like a bolt is going to hit something on the rest of the robot, but we'll figure that out later if we put it into a main robot assembly, right? So now we want to draw our motor. So, well, not draw our motors exactly, but where our motor is going to go. So our motor is going to sit on somewhere over here, because essentially we want it to be inside of the robot when our intake is out. If it's outside the robot, if it's over here, it could mean that another robot will come and hit it. One of the wires will get cut. A connection could be disconnected. All sorts of like not great things. So that's why we want to keep it. Ideally, the motor is as safe as possible, right? Which is why I'm going to keep it over here, for example. Now we need to figure out how far the motor is going to be from this guy, from our first roller. Essentially what we're going to have is, I think we spoke about this in the last video, but we're going to have a belt going here and a belt going here, there to there. But the first belt, that powers all the rollers, needs to be going from there to there, right? So we're going to dimension these two. Oops, not what I wanted. Going to dimension these two. And we're going to go back to recalc to the belt calculator. What do we think of? I don't want this yet, just in case. It could be on that line. You know, it doesn't necessarily have to be, but I'll just leave it off just in case. So let's say it's going to sit somewhere around there. Target center 160 mil. That's our dimension here. We're going to do a. Oh, right. We're going to use a near vortex. So if we use a near vortex, it means that we can use a Kraken pulley. Why can we use a Kraken pulley? They are different motors. The Kraken is this guy here, right? Kraken is this guy here. The near vortex, it looks a bit different. It looks like this, right? They have a different shaft output. The nice thing about the vortex is you can put any shaft you want in, any of these, I guess. So we're gonna go vortex shaft 15-2. 15-2 spline. Now, what is the 15-2 spline? The 15-2 spline is compatible with spline XS shaft components. That's great because the Kraken also has spline XS. Perfect. So we're going to use this guy. Sounds good, right? Doesn't really matter. You could use that guy. They're just for wider belts. We're going to stick to this one, which has this Kraken hull. So go back to recalc. 12, let's say 24, 12 to 24, where the motor is going to be driving the 12 tooth and the roller is going to have the 24 tooth on it. We can take a look at what it's suggesting for us. So we can either go with a 154 or 167. How does 167 look? Yeah, good enough, you know, like. Now we just need to be a bit careful that our sprocket doesn't hit the motor, since they are quite close. So what I'll do is I'm going to draw a construction line, which is going to represent the outer diameter of the motor, plus a bit more for some clearance for the chain, right? Because the chain also needs to go around. So what do we say? 36? Yeah. I guess it doesn't matter, it's just got the table. Outer diameter with chain. Oh, perfect. 4.65. So I'm going to change this guy to 4.651. I already know it doesn't fit. Yeah. So the motor needs to stay out of that. That's fine because we can just move him here, right? And now the motor is super clear of the chain and the sprocket. It's also, you know, I could also use this dimension where I use the 80 tooth belt. So 154.7053. But you know, doesn't really matter actually. They are pretty close to each other, but you don't want to come outside of the robot, right? Yeah, I might just stick with that. Why not? Doesn't really matter. Okay, so we've got that. That's gonna be our motor. Our motor actually. Oh, I forgot. We need to like, you know, put a dimension in that will represent like our motor diameter, because we don't actually know if our motor is hitting. That was very stupid of me. So let's go vortex. We need to figure out what the diameter of our motor is. Body mounting footprint rounded side. Okay, the docked mounting footprint rounded side diameter is 60 mil. So you can be 60 mil. We just need to make him clear. Those two circles clear. Perfect. What else do I want? I want to have access to the end of the shaft, right? Because if you look at like the Kraken shaft, you should do this anyway, because you want to be able to slide the pulley on and off when when the motor's on the intake. See how the Kraken shaft has a thread at the end? That's because you put your pulley on and then you put a bolt to stop it from sliding off. So we want a hole to make sure that we can tighten that bolt. And you know, it would be really nice if the hole was big enough so that we could slide the pulley off if we needed to, so that we didn't have to completely take off the motor, take off the pulley, put a new pulley back on, and then put the motor back on. Right? Instead, we can just dimension this guy to be the diameter of the pulley plus a little bit more so it can fit through. So what's the diameter of a pulley? You know, we can go back into here and we can find out. We're going to be using this guy, so we'll go to PDF. Spline excess pulleys. Their outer diameter is almost 1 inch. Let's just make it 0.95 inch, right? And now that should be able to come out through that hole. The next thing that we're going to want to do is do the mounting holes for the vortex. So the mounting holes for the vortex, if you read here, the vortex docks, no, that's the docking. That's the vortex, it actually has two pieces. It's got this spark flex, and it's got the motor itself, which is this guy. I go into here, you can see this. Yeah, so this guy mounts onto the front of this. That's the motor controller, that's the motor. This sends the current to the motor so that it runs. But essentially, we want to know what the actual motor mounting, if we want to mount it to a plate, how do we do that? So it should say somewhere here, 1032 threaded holes in a 2-inch bolt circle. 1032 is practically M5. I call it the imperial version of M5. So we can do that. So this, there's how many holes are there? 1, 2, 3, 4. Right? I think that's 4 holes, right? So we'll do 4 holes. Okay. Like before, we'll just do the circular pattern. Move our center point there. Times 4. Cool. They can be 5 mil in diameter because we said that 1032 was practically the M5 for Americans. So that can still move like this. Our holes can also move, right? Oh, I accidentally put that circle on our motor perimeter instead of a 2-inch bolt circle. So let's undo that. So we want to draw a 2-inch bolt circle. Construction line. Same thing we did before, 5 mil. Should actually make all these holes 5.1 for clearance. But it'll probably get drilled out by 5 mil drill anyway. Actually, I don't know what the CNC guys use. And then circular pattern, like before. Times 4. What I'll do as well is I'm gonna line up one of the spaces to be on the line between the motor, like where the belt runs, because I want the belt to go around it. So that's now constrained to there. This needs to be dimensioned to 2 inches because we're on a 2-inch bolt circle. Great. We've still got this issue, right? I'm going to dimension these guys off each other so that there's a set clearance at all times. 5 mil. Might be too little, probably fine. Just gotta make sure the wires don't point right into the sprocket. Cool. So now, what other holes do I want to have? I don't think there are any other holes. So now we can draw a plate. I'm gonna make a new sketch for that, just to clean it up a bit. Oh, yeah. I'm gonna make a new sketch on the right plane. Yep. I'll hide this guy because, yeah, I'll hide him for now because I don't really care about him. And I'm going to start dimensioning. You know what? I've changed my mind. I want this guy to be 25 chain. It's a bit smaller. It has less of a tensile load capacity, so it means that it can, chain. It means that it can take less load, but it means that my sprocket will be much, much smaller, which I think it's a bit excessively big right now. So I'll go to 25 sprockets and a 36. Do they sell a 36 chain? Yes. So this guy here. I want to know what the bolt circle is. I want to know all this stuff about it. So again, I can go into here. I'll find out what the product code is. 54. That's not. Oh, that's not even the right product code. Okay. Doesn't matter because their bolt circle should still be the same. The bolt circle between 32 and 25 should be the same anyway. 50.8, yeah. It's all the same bolt circle. But I also want to know what the reference diameter of it is, the reference outer diameter, when you include the chain. 36, 3.095. 3.095 inch. Much smaller. That's great. Cool. So now I can sketch the rest. Yeah. Sorry, I'm gonna do it all in one sketch because I want to. Wait. Sorry, I've changed my mind. I'm gonna do it all in one sketch, just so it's a bit easier. Don't have to make it messy in terms of like having it in multiple sketches. But you know, if your sketch is especially cluttered, you might want to consider doing your other stuff in multiple sketches. This is not too bad, so I'm just going to do it all here. So what we do is we draw center point arcs around everything we want to kind of like draw the perimeter around. You know, this point, this hole here, you know, it doesn't really have an effect on the perimeter, so I'm not going to draw an arc around it. But this guy probably will. Maybe even this guy. The rollers definitely will. The arcs will go like the perimeter will be something like this. Oh, I put a constraint there I didn't want. Just like that, right? Now I want to draw some lines in between all those arcs. Like that. Those lines are going to make up my perimeter. At this point, what I probably want to do is just kind of roughly sketch out. I don't want to make it horizontal. You can see it's going to put that horizontal constraint. I want to, okay, whatever. But you know, you can see here, if I was to put it there, it would constrain that point to be like it would constrain this line to be vertical, and it would constrain that point to be vertical to that dot there, which I don't necessarily want. They have no relation to each other. So I'm just going to drag it out a bit more and get rid of that magnet feature. And back down here. Now what I want to do, it looks kind of ugly, I agree. I probably want to make all of these things, all these lines tangent, so that they kind of flow nice. So how do I make them tangent? I can use this tangent feature. Make a tangent relation between two sketch entities, between a sketch entity and a plane. Cool. So I click T to use that. Make this guy and this guy tangent. All the arcs and the lines that need to be, you know, if the line is touching an arc, they need to be tangent, just like that. This one as well. This guy. Cool. I probably, you know, you can still, if you drag around these blue lines, you can see how things are still kind of unconstrained. I probably want like the roller arcs to be equal. So I'll make those equal. I can probably also define the roller arc diameter now. When I say roller arc, I'm talking about the arcs that are defined off the roller. So what I will do is I'm going to dimension the roller arc diameter to be 2 mil offset from my roller in that direction. Now, why am I doing that? Because if our intake was to come in and hit a ball, right, and we had the plate kind of sitting outside like that, if the ball hit like the edge of the intake, it's just going to hit the plate and bounce off. It's not going to hit the roller. It's not going to be sucked in by the roller. By doing this, it's 2 mil. When the ball comes and hits the intake, no matter where, it'll always touch a roller and kind of like be sucked in, which is what we want. So that's good. Yeah, you can see it's done that for all of them there because we made our arcs equal. Not that I care about this one all that much. Maybe actually this one and this one and this one and this one shouldn't be equal because it means that, you know, this doesn't have as much material around it and I don't really care whether this roller is exposed. So you know what, just for the case, for argument's sake, I will get rid of those. And I'm just going to make them equal to the roller diameter. Make it aligned. It'll look nice. Cool. So I still have this. I have this. How am I going to determine the diameter of this arc? Probably going to do... I'm going to make sure that the distance between these two is sufficient in terms of material. If it's too close and you know there's a force in this direction due to, I don't know, the intake gets hit and there's a force on this hole, it could crack. It could snap this hole because it's so thin. So I want to make sure there's enough material there. So on this guy I'm going to put 4 mil material. What's that? 4.14. That's good, right? Probably going to want to do the same for him. So this one will probably not experience the same forces because it's not the one that's holding the intake to the robot. So I'm going to put that at 3 mil. Yeah, cool. So at this point, you know, it's not fully defined. I still have some more. I guess I could also do this guy here. If I do 3, does it still look good? Nah, it looks kind of bad. So I'm going to keep it at 16. That looks all right. And I can still change this up. You want to kind of keep this plate kind of beefy, just in case, you know, this plate is sitting outside of our robot. It could collide with a wall, it could collide with another robot and experience a lot of force. So you don't want it to be too thin. You know, like if it's like this, it might snap. You know, the thinner it is, the more flimsy it is, the more likely it'll snap. So I'm just gonna put it around there and we'll figure out how we're gonna dimension that later. But I can extrude this out, make that 6 mil. Yeah. On top of that, we can also, you know, this is like a sharp corner. Doesn't look nice, you know. So what I'll do is I'm gonna do a fillet. A fillet creates a edge fillet. That's pretty much just a radius in your corner. So if I put a fillet there, I can increase that radius to be, let's say 10. And yeah, now it's rounded. And that's actually really good for our stresses in our plate. If I look at fillet stresses, you can see that the stress concentration in a non-filleted edge, you have a lot more stress in that corner than you would in a filleted edge. The fillet increases the strength of your part, right? So we always want to put fillets, especially in a plate like this. Yeah, so I can go back into here. I suppose I can dimension this angle, say 145. What's this guy? Yeah. And how do we want to determine how long this is? Ideally, you want to have a meaningful dimension in terms of like this. If I was to dimension like this number should mean something. There should be a reason it's 100 mil. It shouldn't be arbitrary. But right now, I can't think of something, so I'm just going to leave it like that. It's the same for these two dimensions. I don't have a reason for them to be 145 degrees and 100 mil. This guy too. I have no idea. You know, this could be anything. It could be 15. It still doesn't matter. But that's okay. But ideally, you'd have those meaningful dimensions. Real quick, I just realized some issues. I'm filming this after I film the rest of the video, but pretty much when we dimension this 5 mil, it actually breaks the CAD almost, because if you were to go and change your master sketch pivot point here to 70, for example, and we version that, and then we wait for the version, and then we go and update that, see how that hole moves. It's not supposed to happen. We definitely used that feature before, so that everything should shift with it. So what the problem is this guy is stopping it from moving. So we'll delete him and we'll replace him with something better. I guess you just need to eyeball that your sprocket isn't going to hit your motor. But let's just say I want my motor to be at least 15 mil away. Yeah. I also realized you probably want to instead dimension this one. So you have like the thickness that you're happy with here. And I suppose you could do the same over here. 125, let's say. And yeah, there you go. It's all dimension now. To something that I'm a bit happy with. And now what I really wanted to demonstrate is I can now change any of my roller positions, 280 for example. That wouldn't work anymore because you can see it's not hitting the ball, it's not super optimal. And go and update that. And you can see it all updates. It's exactly what we wanted. We want like CAD that's adaptable to whatever we want to do. If we want to make a change, it should take 2 seconds, just like that. Right? Create version. Great. Now looking at this again, yeah, updates like that. But yeah, like I was saying, looking at this again, I feel like there's things that I would want to change. Maybe I might actually do it now. I might just beef up this guy over here, give him a bit more material, maybe increase this angle, 135. Maybe beef this guy up a bit to 7 mil. Even more. Yeah, I'm not so sure if I'm happy with the shape, but it's up to you. And in the end of the day, what you really need to do is get this part cut, get a prototype made, and ram it into the wall and see if it holds up. Because you know that all the belt positions are fine. We can test the intake to see if the ball goes in with all the belt positions. But what I'm concerned about here is this intake going to withstand a hit from the wall? But yeah, you just need to ram your intake into the wall and see what breaks first. But anyway, yeah, thanks for watching. In the next episode, we'll probably be working on some the pivoting system. We might even start assembling some of the components, and we'll be making some auxiliary stuff, such as like the spaces to mount the motor, the spaces to mount the sprocket to this plate, the spaces for our pivoting gearbox system. But yeah, thanks for watching.